This CFD training package includes 7 different products related to the chemical engineering, such as bluff body milled burner, hydrocyclones, fuel cells, spray dryer, diesel spray injection, gasification, and also gas liquid separator. Also, the CFD simulation results are compared and validated with the related papers. By clicking on the subscribe button, you will be informed about the newest CFD training videos by Mr. CFD. Or if you are watching the training video, click on the Mr. CFD logo and subscribe.
In this project, we will simulate a bluff body mild burner. A new window will appear showing you the dominant extents of your geometry. Also, under the view length unit section, you can see the default geometry units, which is meter in this project. Also, under the scaling section, under the mesh was created in, you can change the settings in order to activate the scaling factors beneath that. For example, your geometry and mesh was designed in a software which its default unit was millimeters. By activating these scaling factors, you can change this factor to your desired factors in order to set the length to the appropriate unit. The Control tab contains the parameters for exclusion and inclusion of equilibrium species. After clicking on the fuel inlet, you can see that it is also been defined to be a velocity inlet boundary type. And by clicking on edit and then in the appeared window under the momentum tab, you can see that the velocity magnitude of the fuel entering this boundary is equal to 1. After that, if you click on the thermal tab under the thermal condition, you can see that we have defined the heat flux condition, and the rate of heat flux applied on this boundary is equal to 0, which means that this wall is adiabatic. And finally, in the oxygen mass fraction contour, you can easily see the oxygen has a higher mass fraction in the sections near the air inlet. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide. In this project, we will numerically validate the data obtained by the paper named Effects of Curvature Radius on Separation Behaviors of the Hydrocyclone with a Tangent Circle Inlet. Under the General Setup tab, you can see different buttons from scales to units. By clicking on a scale, in the appeared window in front of the gauge pressure section, you can see that we have defined 0 gauge pressure, which means that the flow will exit this boundary to the atmosphere. After double-clicking on the Residuals button, a new window will appear. In the appeared window, you can see the absolute criteria for equations like continuity, x velocity, y velocity, and so on. Now, when you set the software to start the simulation, there would be error between each iteration. Now, if that error is less than these criterion, it conveys the meaning that that equation has reached convergence. Now, in order to extract 2D contours, we first have to define a plane where we want our 2D contours to be shown. In order to do that, you can see that under the surfaces section, we have defined a plane 7. By double-clicking on it, a new window will appear. In the appeared window, you can see that under the method section, we have selected point and normal. Now, if you enter these specific values and click on Save button, the software will create this plane for you. Now in this slide, you can see the contours of volume fraction of air, and you can compare this contour with the contour presented in the paper. It should also be noted that just like the paper, there is an air core in the middle section of our geometry. And finally, in this slide, you can see that in this graph, we have compared our CFD simulation results with the result presented in the paper, and you can see that good agreement exists between our results and the papers. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide. In this project, we will numerically simulate the electrochemical process which happened inside a fuel cell using ANSYS FLUENT software. A new window will appear showing you the dominant extents of your geometry. Also, under the view length unit section, you can see the default geometry units, which is meter in this project. Also, under the scaling section, under the mesh was created in, you can change the settings in order to activate the scaling factors beneath that. For example, your geometry and mesh is designed in a software which its default unit was millimeters. By activating these scaling factors, you can change this factor to your desired factors in order to set the length to the appropriate unit. In the tab Settings for anode and cathode in the fuel cell module, areas related to building a fuel cell must be defined using the zone or areas in the model. The fuel cell consists of 4 areas, including the current collector, the flow channel, the porous electrode, and the catalytic area (TPB) layer, each of which is for both the cathode and anodic portions. Thus, according to the symbols already mentioned for naming districts, the area should be defined for the zones in the following headings. In the appeared window, by clicking on Fluent Database button, a new window will appear in which you can select a new material from a list of material available in the Fluent software. As was previously explained about the water content in our anodic and cathodic channels, you can see that under the Fixed Values tab, we have set the value of water content to be equal to 0. In the appeared window, you can see that we have again defined the material name of FC mixture. We have also enabled source term and fixed values and porous zone options. By clicking on UDS tab, under the user-defined scalar boundary condition, you can see that for all of the options, specified flux has been defined. Now, under the underdefined scalar boundary value, you can see that for all of the options, the value of 0 has been defined, since we have previously explained that for all outer boundaries, these values would be equal to 0. After clicking on this boundary, you can see that under the thermal and UDS tab, coupled condition have been defined, which means that this wall is in contact with the fluid on its both sides. You can see that under the user-defined scalar boundary condition of electric and protonic potential, the setting of a specified value and a specified flux respectively have been defined. Now, as was previously mentioned about the outer boundaries, which have the electrical and protonic potential of 0, you can see that we have defined those values in this window. After clicking on this boundary, you can see that under the thermal and UDS tab, coupled condition have been defined, which means that this wall is in contact with the fluid on its both sides. After clicking on this wall boundary, you can see that heat flux thermal condition has been defined with a heat flux rate of 0, which means that this wall is adiabatic. And if we click on UDS tab, now in order to extract the mass fraction contours of hydrogen, we select a species under the contours of section, and underneath it, as said before, we select mass fraction of hydrogen. After that, by clicking on Server Display button, just like the previous steps, the software will show you the contour. Here in this slide, you can see the electric potential changes in our computational domain. You can see the changes of electric potential in the middle membrane and how it has changed from the value of 0.5 to the value of almost 0. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
The product number 4 simulates a spray dryer using ANSYS FLUENT software. In the present modeling, we use unstructured mesh. The total element number is equal to 84,047. In the inlet and outlet zones, we use a more accurate grids. In the near wall treatment option, we select the standard wall function. Because if the K epsilon turbulence model is used like in this simulation, it is not possible to simulate flow vortex near the walls. So a wall function must be defined, that is a standard wall function for this simulation, to investigate the fluid behavior near the wall. The mass flow is equal to 0.0116. Then let's go to the thermal boundary condition of the wall of the cyclone. The thermal condition is convection. The heat transfer coefficient is equal to 3.5. The free stream temperature is equal to 298.15 degree of Kelvin, and also the wall thickness is equal to 2 millimeter. And finally, we should check the material of the wall, that in this case, the material of the wall is steel. In this simulation, we select the hybrid initialization method since there are two inlets and just one outlet, and the hybrid initialization seems to be a better method. Also, we can check and see the velocity vectors in the central plane in the cyclone.
In this project, we will numerically validate the data obtained by the paper named Spray-Induced Air Motion in Single and Twin Ultra-High Injection Diesel Sprays. A new window will appear showing you the DOM and extents of your geometry. Also, under the view length unit section, you can see the default geometry units, which is meter in this project. Also, under the scaling section, under the mesh was created in, you can change the settings in order to activate the scaling factors beneath that. For example, your geometry and mesh was designed in a software which its default unit was millimeters. By activating these scaling factors, you can change this factor to your desired factors in order to set the length to the appropriate unit. After clicking on Edit button for the inlet boundary, which refers to the boundary where the particles are injected in our computational domain, you can see that a new window will appear. In the appeared window, under the Momentum tab, you can see that a stationary wall motion and no slip shear condition is defined. Now in this contour, you can easily see the velocity distribution in our computational domain. Also, you can easily see the section where the particles are injected in our computational domain and how it has an increased velocity in comparison to other sections. Now, as was mentioned earlier in previous slides about the penetration length report we had defined, when you click on the Calculate button and when the software starts solving the problem, it will automatically show you the red line shown in this figure as it continues to solve the problem. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
The present problem simulates the gasification process inside a gasifier chamber. From the scale mesh section, we can check all the domain extents in every direction and the dimensions. Also, we can view length unit. In the near wall treatment option, we select the standard wall function. Because if the K epsilon turbulence model is used like in this simulation, it is not possible to simulate flow vortex near the walls. So a wall function must be defined, that is a standard wall function for this simulation, to investigate the fluid behavior near the wall. Here is the temperature contour. As it is obvious, the temperature starts to raise up from the middle inlets to the top because of the higher temperature and the combustion that occurs after the middle inlets. A summary of the defining steps of the problem and its solution is given in the following table as a review.
In this project, we will simulate a gas-liquid separator using ANSYS FLUENT software. Next, right-click on Mesh and then go over Import Mesh File. Now, as was mentioned in previous slides, in order to add a new material, all you have to do is to expand Materials and then right-click on Fluid and then select New. Same can be said for the oil region, and you can see here that the oil material is selected under the Phase section. After clicking on Edit button, in the appeared window under the Momentum tab, the most important point you should pay attention to is the gauge pressure, which has the value of 0 pascal, meaning that our liquid or gas flow will exit our computational domain to the atmosphere. After creating your desired plane, then click on Contours button and accept the appeared window. And finally, to extract the streamlines, just click on the Streamlines button and accept the appeared window. And finally, in this slide, you can see the streamlines for both oil and gas phases. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
Obtain the mesh file and also the full training movie by purchasing this product. To benefit from Master CFD services including simulation, consultation, and training, contact our experts via info@mastercfd.com.